gentlemen. How are we doing today? Wonderful, wonderful, wonderful. Great, awesome, incredible. Joshua, grab a pencil. Grab your periodic table, grab a calculator. Let's go. All right. Sure, just throw my calculator on the ground. It's okay.
Look gloves. Oh, see. Wait. I'm gonna use size.
Oh, you copied me. I had it. Oh, I already had it.
Oh yeah.
Oh yeah, exactly.
I'll be balling out.
No, you did.
Bro, this will protect me from
You were
anything.
still doing it. Exactly, but you didn't order
Balling
it.
out.
Michael Jackson, take off the glove. You don't need it.
Oh, okay, my bad.
But I had to go.
I got called Michael Jackson. I feel honored.
Achilles, shins up here.
Yeah, no, I think that's so I think it's worth it. You think so? No, wait. No, I don't think so.
Yes, and they're like,
I thought answers were available. I'm very curious.
All
Eddie,
oh God.
Me
too. I was
I think it's a
Case.
no.
I was so happy because I was stressed. I didn't know.
Wait.
There's three. Did I not?
Oh.
We've been doing
It was Barbara too.
Everything else right though.
Dang, I don't know.
Please.
I don't think
Wait,
it's
why
your
do you
math.
think
Bad. It could be your math. Then just ask.
This part up here.
This is
in there.
Maddie.
No. Yeah, it's 3. But I rounded up.
Thank you.
Why is it left like that?
Yep.
Irving.
It's 3.
Or is it because of
Why?
Or is it supposed to be there?
Stephen.
Oh, wait.
Isn't
Probably.
it usually this one?
That's my guess.
Both the same thing.
And look, I'm so smart. I put this in. Make sure all these zeros count.
It's like there's like well, add it up. Because I have number 5, I can't remember. I don't remember.
Joshua, what can I do you for, sir?
Number 4, the
Yeah.
test, it says that this minus 1.36 but I have it in 3 with everything else.
Okay, let me go through it and I'll explain. Okay? Here, ladies and gentlemen, A or B, here are the answers for the first part. The only thing I will tell you is any place where I have increase, you could have used decrease, but here where they are the same, they would both have to be decrease. I don't care which one you said. The same thing here. These can be reversed because these are in an inverse relationship. So I don't care which one you said increased, which one you said decreased. And then here, these are in a direct, so they obviously need to be going in the same direction, whichever direction you pick. Okay? So, questions?
My first quiz I've ever raised. Yeah. 20.
Any questions at all? Okay. So I will get to B if you have B, but let me go through A first, ladies and gentlemen. So this is what it should have looked like for number 4. Should have been in 3 sig figs. This is what it should look like for number 5, again in 3 sig figs. This is what it looked like for number 6, and again in 3 sig figs. Okay? You got a point when you did your conversions from Celsius to Kelvin on these, ladies and gentlemen. Okay? Obviously none needed here because there was no conversion there from Celsius to Kelvin. So, anyone have any questions on those 3? I should have done this.
Oh, wait, hold on.
Josh, the reason that number 4 you lost a point on that is because technically there were only 2 sig figs if you look at that problem. The last number, 720, only has 2 sig figs. So, that's why. Okay? So, questions?
It's the same answer.
Can we keep these?
Yes. Yes, you may.
Thank you, sir.
Ready?
How much did you get? 20?
And I do understand that I did say many times most of them are in 3 sig figs. That one just happened to work out where it wasn't. Sorry. Okay. Questions, ladies and gentlemen? Okay. All right. Then, with that in mind, ladies and gentlemen, welcome to Monday. Our first Monday together this year, ladies and gentlemen. So,
Yes, no, it is. It is.
yeah, we didn't have Monday last week that we were together.
Wait, and then it's next week. We don't have school Monday, Friday.
Next week you don't have school on Monday. Next week you don't have school on Friday, and the week after that you don't have school on Monday.
You think we're gonna get a snow day this week? Tomorrow?
I hope not.
Or at least a 2
By the
hour
way,
ride.
probably not tomorrow.
That's ridiculous.
Tomorrow the snow's not supposed to start until the afternoon.
Oh, well, Wednesday. No,
Let's hope not. What?
It starts tomorrow morning.
The weather forecast I heard said the heaviest snow is supposed to be tomorrow afternoon.
I heard all day. Where they do like 3 guys.
Why?
TB,
She wants to be.
you and I are not going to have this conversation because you have already wanted to change the school year so that we go to school in the middle of summer and we have off in winter. So your whole viewpoint of this thing is skewed beyond belief in the wrong direction. There is no way I want to trade a day off in May when it's sunny and could be nice for a day in January when it's snowy and freezing. That's just cool.
Stay inside and snow.
Spring break.
If you want to stay inside and let it snow, what better place to be than at school? Because it never snows in this building.
I mean, it might.
So. All right, anybody have an exciting part of the weekend they want to share with us?
I met Jordan Love.
You what?
I did Packer Park. Okay, Packers won.
Okay, I did see that, yes. Yes. Yeah, okay, yeah.
Pretty solid liquid glass and plus.
Any other exciting things happen? No one won the lottery, inherited money from a relative who passed away who you didn't know you had?
Did you?
No. Most of my relatives are poor. I'm not getting anything from them.
I went to Target.
So I went to Target too
Really?
on Saturday, Sunday morning. Yeah, I went to Target
I went to
because my wife forgot to pick up a birthday card for her mother, so we had to go get it on Friday or on Sunday. All my wife's fault. Otherwise, I could have just stayed at home all day, done nothing. All right. Today, then, ladies and gentlemen, since you people are the most boring people in the world, I will be able to understand and use ideal gas laws to solve problems. Okay? So, I got a new packet for you today, ladies and gentlemen.
Yeah.
More wasted tree.
This is not a tree, in case you didn't notice. This tree died for your education, Christopher. You should cherish it. You should do the entire packet and know all of this stuff. Otherwise, you have made this tree's life worthless. And that is on you, sir, not on anyone else. You do it?
Doo-doo.
Yeah, I believe you're full of doo-doo.
Get him on the phone. I think you should now.
That's mine. You just said it. On everything that you make it do that one. I swear.
Why is not there? You realize that it's on the lead.
Abby.
In the
No, you gotta go in the bank and grab it from there.
Okay,
Ooh, they have real options.
now I want you to take a real close look, ladies and gentlemen, at that first page at the top under the formulas to use. We have learned some of those formulas. We have not learned all of them, but we will put them all on the test for you.
Why?
Because that way we know if you know how to use them.
Can we go through them and label which one's which?
What?
Can we like go through which one's which?
You can put any labels you want on anything you want. 100% up to you. Okay?
Oh, yeah. NRT. NRG.
All right. So, again, ladies and gentlemen, we will go through all of these formulas with you. We will talk about all of them. Okay? Oh, and by the way, on Wednesday, we will have a lab this week where you need your goggles. So if they're here, great. But if not, on Wednesday, you need to bring your goggles with you so that you can do the lab on Wednesday. Okay? Quite possibly next week we'll be taking the unit test. So Unit 5 retakes got to be done by the end of this week. Thursday's the last day for them. Okay? Thursday's the last day for them, ladies and gentlemen. So get your butt in here if you want to get them done. Bring your test corrections with you, because if you don't show me test corrections, you don't get to do the test. All right. Excellent. Excellent. All right. So here we go, ladies and gentlemen. First of all, before we get into ideal gas law, this is a summary of the 4 gas laws that we introduced to you at the very start. Boyle's, Gay-Lussac's, Charles, and Avogadro. Each one deals with 2 variables. Each one holds 2 things constant. The only inverse relationship is Boyle's. Every other one is a direct relationship. And if you'll notice in the formulas, ladies and gentlemen, P is on top of every formula that it is involved in. V is on top in every formula it is involved in, and T is on the bottom of the formulas it is involved in, meaning all of these things never change places. All of these things always go in the exact same place, okay? Now, these are gas laws that we can use when we are talking about only changing one thing and seeing how something else reacts to it. Only changing the volume and seeing what happens to pressure. Only changing the pressure, seeing what happens to the temperature. Only changing the volume and seeing what happens to the temperature, or only changing the amount of gas and see what happens to the amount of space it takes up. These are what we use for those things, ladies and gentlemen. The next page shows the combined gas laws, which puts in 3 out of the 4 variables, only holding the amount of gas constant. The relationship is both inverse and direct. Why? The inverse relationship between pressure and volume that was in Boyle's law is still here in combined gas laws. The direct relationship between pressure and temp and the direct relationship between volume and temp still exists. But what this means, ladies and gentlemen, is because you have 3 things changing, it is possible that one change could be additive to another. In other words, they both say go up. and they both make it go up more than it would have individually. They could work against one another, and they could literally cancel each other out. This one says to go up by so much, this one says to go down by so much, and maybe nothing happens. Maybe it doesn't change in the end, okay? Or one of those changes could be more powerful than the other. A change in pressure might be bigger than the change in temperature, causing the volume to decrease instead of increasing, okay? But the only way we can do these is to actually work the problems, okay? And when we work the problems, ladies and gentlemen, this is the formula that we will use. However, this one takes the place of 3 of the 4 on the other page. This one formula takes the place of Charles, Gay-Lussac's, and Boyle's law. The only difference is if you work one of those gas laws and something is held constant, we would simply either do one of 2 things. Put the same number in for what is held constant on both sides. Easiest number to put in would be 1. 1 liter, 1 Kelvin, 1 atmosphere of pressure if they're held constant. I don't care which one. And then you could still work this problem, or simply take it out of the equation. So if pressure is held constant, remove it from both sides, and you are left with Charles' law. Your choice. I don't care. This is one of the ones on the sheet. So Josie, if you want to label it, first one on the top left, combined gas law. That's what it is. By the way, what would you label those things at the top above combined gas law? Standard pressure. By the way, might also be a good idea, ladies and gentlemen, to up there, you're going to put standard pressure. We also might want to make a note of standard temperature. Which is? That's a volume. 22.4 is volume. I heard, I didn't hear what your... 273 Kelvin, which is what we would have to use in our gas laws, because if temperature is in there, it has to be in Kelvin. But that is actually 0 degrees Celsius, ladies and gentlemen. That is the condition that we would work with standard pressures at that standard temperature as well. Okay? Questions? Okay. So again, just a couple notes that will help you out with some of these. Okay? Now again, some of these formulas, we'll introduce them all to you. We will go through them all. But again, any idea what M stands for here? What?
Mass.
Absolutely correct. Mass. Any idea what V stands for here? Nope. That would be a capital D. What?
Velocity.
Velocity, yes. This is velocity. Okay? So what is this D here?
Density.
Very good. So we've already got an idea that there are gas laws that relate mass of a gas and its velocity, density of a gas and its masses, pressures of a gas and the amount of moles of the gas. Okay? So again, some pretty obvious gas laws, but again, be careful. Small v different from the big V up here. Okay? Questions? All right. All right. So today we're going to talk about something called ideal gas law. And ideal gas law is what we have been building up to all of this time. Ideal gas law is the gas law if absolutely nothing is held constant. Nothing. And you can work problems if nothing is held constant. And about 99% of the time, ideal gas law holds true. Ideal gases behave as we would expect them to. There are a couple of times when gases do not behave as we would expect them to. under certain conditions of pressure, volume, and temperature. What condition of temperature do you think could mess gases up?
Freezing.
What?
Wait, that's gas.
Okay, but you're on the right track.
Negative?
Nope.
But it does the phase change thing.
When you get close to a phase change. In other words, gases will normally behave the way they are supposed to. Unless you, now to get near a phase change, what do you have to do to gases? Think about what state they're in. Think about how they would go to the next closest state. So gases are obviously in the vapor state, right?
You have to cool them down.
Have to cool them down. So ideal gas law says that gases normally behave the way they are supposed to. One time when they would not is at extremely low temperatures. When the gas is about to change to a liquid, they may not behave the way they are supposed to. We're going to ignore that most of the time. Okay? Now, volume doesn't affect the gas in terms of ideal gas law, but pressure does. What kind of pressure would mess up a gas? What kind of a pressure do you think would... You got two choices. What? Low pressure. Okay, but in low pressure, the particles aren't going to hit the walls very often, right? High pressure, they're going to hit the walls all the time, right? Which one would mess it up? High pressure actually will mess up gas laws because you're forcing, under high pressure, you're normally forcing the particles to be very what to each other? Close. They're moving around so fast, they're creating a lot of pressure, right? So they have to get closer to each other. Guess what happens if gas particles get closer to each other? What can take over? By the way, the same thing takes over at extremely low temperatures. Forces of attraction start to act. One of the things that we ignored forces of attraction was because the particles were spread out and they were moving very fast, correct? Well, at low temperatures, are the particles moving very fast? No. So all of a sudden, it becomes harder to ignore forces of attraction because when particles hit each other, now they want to stick together. They want to start making a liquid. Well, under extremely high pressures, because they are so close together that sometimes it's harder to ignore those forces of attraction as well. Okay? Sometimes it's harder to ignore those. Okay? This is the formula for ideal gas law. PV equals nRT. Now, where it actually comes from, ladies and gentlemen, is something that we showed you last week. So let's take a look at this real quick. Okay? Now, this is combined gas law. P1 V1 over T1 equals P2 V2 over T2, correct? Now, the only thing missing from that is what variable? N. Where does N go? N goes in the bottom. So we could put N1 here and we could put N2 here, okay? Now, for this formula, ladies and gentlemen, we are comparing one set of conditions of a gas to another. That's what we've been doing all along. Hey, here's a pressure, here's a volume. If we change the pressure to this, what will our new volume be? So we're comparing conditions. Here was the gas originally, here was it when we changed it. Well, the one thing that we can do with these is we can always compare back to standard conditions. So if we compare back to standard conditions, ladies and gentlemen, what are standard pressures? What are they? What are the numbers?
14.7.
Go.
760 mmHg.
Okay.
101.3 kPa in 1 atmosphere.
So there are only 4 numbers that I can put into here. I take that back. I've only given you 4 numbers to put in here. because I have given you the four most standard units of pressure. Are there other units of pressure out there? Yeah, just like there are all kinds of units out there for measuring anything, right? I didn't give you every single unit of pressure on Earth, okay? I gave you the four most common, okay? But if we are given a pressure, if it's in atmospheres, then I'm going to put pressure in here in atmospheres. If I'm given a pressure in kPa, over here I'm going to put in pressure in kPa. Because again, it doesn't matter what units we use as long as they are the what on both sides? As long as they are the same on both sides, okay? As long as they are the same on both sides. All right. So then, ladies and gentlemen, we have temperature. Now, temperature also can only be one number at standard temperature. What is that? 273 Kelvin. So I don't care what the temperature is over here. We could compare it to a standard temperature of 273 Kelvin. We know what the pressure would be at that temperature because they're up here. So these pressures go with this temperature, okay? Now the hard part about this is this part right here, V and N. Because if we put more gas in, what happens to the volume? Even at standard pressure and temperature. If you put more gas in, the volume is going to get bigger, okay? But, ladies and gentlemen, if we look at it a little bit more closely, pick an amount of, oops, sorry, wrong one here. That's not N, that's supposed to be, or T, that's supposed to be N. Sorry. Pick a number of moles. Give me a number of moles. 3. If you have 3.0 moles, how much volume will it take up at STP? 67.2. And I believe we did this the other day, didn't we? Okay. And I gave a bunch of points. 2.0, 44.8. 1.0, 22.4. 0.5, 11.2. No matter what, V divided by N always equals what number at STP? 22.4 liters over 1 mole. Which means, ladies and gentlemen, these here become this. So in reality, ladies and gentlemen, now there is nothing on this side that ever does what? This always 273. This always 22.4 over 1. Now, again, it might be 44.8 over 2, but that still reduces to 22.4 over 1. So this never changes, right? This doesn't change, and this has to be one of these four, which never changes. That means that this entire side over here, ladies and gentlemen, becomes one true constant. One true constant. A number that does not change. It becomes a constant. All of this here becomes R. R is a true constant. A number that does not change. Okay? So what that means, ladies and gentlemen, is P1 times V1 over T1 times N1 equals R. R, a number that doesn't change. Now, they rewrite this formula so that everything is on one line. Well, to do that, ladies and gentlemen, we're going to take this side of the formula times T1 over N1 so that they cancel out. And what you do to one side of the formula, you do to the other. And that is where this formula of PV equals nRT comes from. P is the pressure of the gas. V is the volume of the gas. N is the number of moles of gas. And T is the temperature. Now, these do not have to be at these conditions because we could have changed them. But we can always compare back to those. And that's what ideal gas law does. Give me the number of moles of gas. Give me its volume. Give me its pressure. I'll tell you what temperature it's at. Give me the temperature, the amount of gas, and the volume. I'll tell you what its pressure is. Give me its pressure, amount of gas, and the temperature. I'll tell you what volume it has to take up. I can now solve for any one of these using this formula. Any one of these. Now, technically, if you even wanted to, you could go back and use it to solve for Boyle's law, for Charles' law, for Gay-Lussac's. It's just there's a lot more work in this doing that. Now, if this is equal to this, and then this becomes R, correct? What do we know about the units for volume here? They have to be the same. But over here for this R, what's our unit for volume? So we can't, no longer can we do milliliters and milliliters. Okay? We got to have liters on this side because this is made up by a number that uses liters. This is made up by a number that uses one of those four. This is in what unit? So this has to be in Kelvin. So now, unlike before where we said it doesn't matter which unit as long as they're the same on both sides, that is still true. But on this side, the only one of these units that can ever change is pressure. Why? Because there are four of them. 4 different standard pressures. Okay? What that means, ladies and gentlemen, is that we can actually figure out, or we actually have 4 different R values. 4 different numbers that never change. And here they are. If I put in 760 for my pressure here, 22.4 for my volume here, 1 for the amount of moles, and 273 for Kelvin, if I solve this for R, this is the number I get, 62.4. Never changes. Never changes. Look at the unit. Millimeters of mercury times liters divided by mole times Kelvin. Why? I'm solving for R over here. Solving for R. T and N need to go back on the other side. That's not the way we write the formula, but that's how we get the R value. If we are using kPAs, 101.3 becomes our pressure. Our volume is still 22.4. Our number of moles is still 1. And our temperature is still 273. So when we use kPa, our R value, our true constant, becomes 8.31. Why are these different? Because of the pressures. That is the only thing different here. This is in millimeters of mercury. This is in kPa. Every other part of the formula is exactly the same. But because we have multiple units of pressure, we get multiple R values. What do you notice about this one compared to this one, though? This one is what? Bigger. Why? 760 is bigger than 101.3. Okay? Now we go down and we put PSI in. Again, the other 3 stay the same. Temperature doesn't change. The amount of gas doesn't change. The number of moles doesn't change. But the pressure does. So now when we put 14.7 psi in there, we get a value of 1.21. Again, a constant, a number that doesn't change. But this is the constant if you're using psi for your pressure. This is the constant if you're using kPa. This is the constant if you're using mmHg. Okay? These do not change, but you need to pick which one depending on what unit your pressure is given to you in. Questions? And there is one more to go. 1 ATM, 22.4 liters, same here, 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 and here. 1 mole, same here, 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 and here. 273, same here, here, here. The only thing different is the pressure. 1 ATM gives us 0.0821. That is our constant. These 4 constant, ladies and gentlemen, if I were you, I would write them down somewhere. I would write them down somewhere, probably on a periodic table that you might use on a test or something. But I would write them down so that you have them, ladies and gentlemen, because those are very important for you in this unit. Now, you could always figure them out on a test. But who wants to waste time figuring out something you don't need to? Just so you're clear, these are the numbers that I would write down. The 4 R values. By the way, it doesn't make sense to write down the numbers if you're not going to write down the units that go with them. 8.31 means nothing to you unless you know that that's what you use when your pressure is in kPa. You won't know when to use 1.21 unless you know that it is for psi. So make sure you write the units with them. Okay? The other way to express this, the way we are more familiar with, would be 62.4 mmHg times liters over mole times Kelvin. I don't care if you write it that way, but these two mean the same thing, just so that we are clear. This could be written 8.31 kPa times liters over mole times Kelvin. This could be written as 1.21 psi times liters over mole times Kelvin. And finally, okay, again, this and this mean the exact same thing. All I've done is instead of using the division sign and keeping it on one line, this would be more how we would be used to seeing it. Questions, ladies and gentlemen? So here's an example of a problem for you. What is the pressure in atmospheres of 0.108 mole sample of helium gas at a temperature of 20 degrees Celsius and its volume is 0.505 liters? Okay. All right. One or 0.108 moles. What is that? PVNT. Which one? That is N. 20 degrees Celsius. What is that? 0.505 liters. What are we missing? Pressure is what we're solving for. We are given a amount of gas, a temperature, and a volume. We are solving for pressure. We should use PV equals nRT. That is the formula that we should use, ladies and gentlemen. That is the formula that we should use. We are trying to find a pressure. We have N for number of moles. We have T for temperature. We have V for volume. Okay? So I am going to take it in this formula. I am going to put in all of these things. P I'm going to leave because it's what I'm solving for. V I'm going to put 0.505 liters equals N is 0.108 moles. Now, what is the R value we are going to use here? Which of those four numbers that you just wrote down on your periodic table do we use for this problem and why?
The 0.0821.
Why, Phoebe?
Because it's an ATM.
Because it is an ATM. And then what do we use for temperature, ladies and gentlemen? Thank you. Please remember, we still need to convert temperature into Kelvin. Temperature has to be in Kelvin. Now, ladies and gentlemen, how do I solve this?
Divide 0.505 liters and cancel the P out.
And cancel the what out?
Like just get P by itself.
Okay, we still want to isolate our variable, ladies and gentlemen. That has not changed. Here's our variable. We need to get it alone. So we're going to take this side and divide it by 0.505 liters. And what I do to one side, got to do to the other. This cancels. Okay? How do I get rid of moles here, ladies and gentlemen? With what? With the mole on the bottom here, this mole cancels out. How do I get rid of this Kelvin? Well, with this Kelvin over here, it cancels out, correct? Okay, liters cancel out, right? What unit am I left with?
ATM.
Which is what I was looking for. So take 0.108 times 0.0821 times 293 and divide by 0.505. Somebody tell me what we get. I'm sorry, go ahead, Morgan. 51.4. Did you get the same thing, Phoebe?
Yes. Yeah, me too.
Good. 51.4 ATMs. Is that a lot or a little bit of pressure? That's a lot. 51 times atmospheric pressure. That is a lot. Still, it is what it is. Questions? Go.
No.
Got it? I guess we're going to find out. You okay? Okay, good. Now, here's the nice part, and here's the reason that they do PV equals nRT, and not PV, P1, V1 over N1, T1 equals R. By putting it all in a line right away, ladies and gentlemen, we don't have to do any of that cross products or equal stuff. It's all in one line. All you're going to do is either solve for P, for V, for N, or for T. By the way, could we solve for R? Why would we ever need to solve for R? What? Cancel out the unit. What do you mean? Why would we need to solve for it? We got 4 R's already. Why would we ever need to solve for R? Why would I ever need to solve for this? This is a true constant, right? Why would I ever need to solve for it?
It cancels out the other units.
I know it does.
Yeah.
But I'm just saying, is there ever a point, we said, in a problem, you might have to solve for T. Gives you a pressure, gives you a volume, gives you amount of gas. Solve for T. You might have to solve for the amount of moles. Gives you a temperature, gives you a volume, gives you a pressure. You could solve for that, right? This problem we solved for P. Gave us volume, gave us amount of moles, gave us temperature, solve for P, right? Could you get a pressure? Could you get moles? Could you get temperature and solve for V? Sure, why not, right? Would there ever be a time when you solve for R?
No.
Never? Never.
We already know
Okay, you're absolutely correct. What's R in Tor?
I don't know.
What do you mean you don't know? You just told me you know all the R's.
You keep them?
What?
I know all the R you keep.
Okay, so are those all the R's in the world?
No.
No. So, what if we had to solve for R? What do we use for volume?
22.4.
22.4. What do we use for moles?
1.
1. What do we use for temp?
272.
And then what do we use for pressure? Whatever the standard pressure is, I give you. I could give you pressure in inches of mercury. I could give you pressure in torr. I could give it to you in bars. There are a lot of units out there. We could solve for R. We would just need the standard pressure to do it. That's how we just found those R's. Was by putting in all the standard conditions. It could be solved for. Okay? Might be a good question on a test to see if you know how to actually do it. See if you know what all the standard conditions are, right? 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 Exactly. How many grams of nitrogen dioxide are present in a sample that occupies 975 milliliters under a pressure of 75.6 kPa at a temperature of 45.0 degrees Celsius? Okay, ladies and gentlemen, what gas law do you think we're going to use? Good choice, since that's the problems we're working on, right? Okay, so I need a P. Do I got a P? I do. More so than you'll ever know, but let's not get into that. Do I have a pressure?
Yes.
Pressure, 75.6. There's P. I need a V. Do I have a V?
Yes.
What is it?
975 milliliters.
Okay. But what's wrong with that volume?
It's in milliliters.
What do I got to do to it? Okay. What is this volume in liters? Somebody please.
0.975.
Perfect. It is the same volume. I've just converted it because I need the unit in liters, right? Okay, good. Do I got an N? Nope, no N. So what does that probably mean? Solving for it. Do I have a temperature?
Yes.
What is it?
45 degrees Celsius.
Convert it. Plus 273 equals 318 Kelvin. So do I have everything I need to solve this? Almost. I do need one other thing. What is it? R. Which R am I going to use here?
8.31.
Why, Phoebe? Very good. So the R is determined by the unit of pressure. Okay? So now I've got a P, 0.975. I've got a pressure for those who hate to hear me complain about having to go pee. We got a V. What is our V? Oh, whoa, 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 whoa.
Oh, you were wrong.
Let's start this one again. What was our P? Sorry.
75.6.
75.6 kPa.
How's the number?
All right. What's our V?
0.975. Liters, yeah.
All right. What's our N?
And
What we're solving for. Good. Let's leave it. What's our R?
8.31.
And finally, what's our temperature?
318.
Okay. So, what do I got to do mathematically here?
Isolate the variable.
Which is N. I want to get N alone on one side, ladies and gentlemen. How do I get N alone on one side? Divide all that. Thank you. Wow, that clarifies things. That makes it clear as mud.
Whatever's on end side.
Divided by 8.31.
Okay.
I really don't want to say on it.
You don't want to say 8.31?
I'm too lazy.
Not hard to believe there. So I divide by 8.31. That it?
At 318 Kelvin.
And what I do to one side of an equation, ladies and gentlemen, I got to do to the other.
That's a nice 3. And then
Just for you, Eric, I will fix it.
thank you.
Only because you're so annoying that if I don't, it'll drive me nuts. Okay.
Oh, we have to solve it now. Oops.
Now, what do you got to be careful with here? Careful with your math. Somebody find me the amount of moles. 0.0278. Is that what you said, Morgan?
Yeah.
Anybody else?
Is this the kind of problem where when you type it in, you have to put the multiplication sign inside the parentheses, or you close it at
On the bottom,
Yeah.
I would do this instead.
Okay.
Multiplication sign there, parentheses in front, parentheses after. Sorry.
Is that just always the case for when?
Yes. Do not put each individual term in the bottom in parentheses because it will treat each term individually then. You might as well not even put parentheses then. Okay?
I got the same thing.
You got the same thing? What's our unit?
How?
Hello? people.
Oh,
Moles of what?
nitrogen dioxide.
Good. Tell me what the formula for nitrogen dioxide.
NO2.
And we are done, correct, ladies and gentlemen? What do you mean no?
How many grams?
What?
How many grams?
I don't know. We just got it into moles. How am I supposed to know how many grams? How are we going to convert it? Huh?
When you use periodic table.
Well, I'm not going from milliliters to liters. I got to go from moles to what unit? Use the periodic table. Periodic table doesn't tell me how to get from grams to moles. What does?
Gram of unit.
What?
The mass of-
The mass of the unit.
the mass of-
Wow, I wish somebody could remember the terminology from the last unit we did. Formula mass. Actually, no, in this case it would be molar mass because NO2 is a molecule or ionic compound. NO2 is a molecule. So, 0.0278 moles. How do I get it into mass, ladies and gentlemen? Put 1 mole on the bottom.
No, like I don't know.
How'd you get 46.0?
One second.
1.
Yeah.
Oh. Three. Oh.
Yeah.
46.
Using what we used in a previous unit later on in chemistry, is that even legal?
So 14.1 plus 32.
Well, I got it. 46.01. I was hoping you were going to give me the answer there.
Oh, well, I thought you wanted me to explain how I got that.
I showed you how we got it right here.
Bad.
If I'd waited any longer, I'd grow old. What is it?
1.27.
Anybody else?
As in there. You want to share or as in yeah.
Isn't it 1.28?
And I got 1.28.
You got 1.28?
Yep.
Josie, did you round correctly?
Probably not.
1.27 what, Josie?
Oh, we're in grant. But
Can you give-
nitrogen dioxide?
Can you give me the number that you got out of your calculator? 1.27 what?
9.
Okay, so then that's going to be 1.
2
grams of
NO2.
grams of NO2, ladies and gentlemen.
We did it
Word,
after a really long.
word date slash long.
Shouldn't have taken that long, but again, we've got 3 people who want to do calculations and 2 people who want to sleep and a bunch of people who want to do nothing other than sit there and talk to their neighbor. and then wonder later on, Mr. Brand, I don't get it. Can you explain it to me again? Sure, I can explain it to you for the 400th time, but if you don't pay attention and listen, it isn't going to do you any good anyway. So, ladies and gentlemen, you might as well see if you can do this. Josie, go ahead. What do you got for me? You certainly can, Josie.
Can I go after Josie?
No, she doesn't want anybody following her.
I want to go after, like when she comes back. Oh, no smart. Oh yeah. Oh, you different.
Okay, ladies and gentlemen. Begin on problem number. Oh, where would be a good place to begin?
I'm doing
Circle these.
You go.
14, 19, 21,
7,
11, 6,
kidding.
I told you 14, correct?
Yep.
16,
Great. Ow.
I told you 19, correct?
Yes, sir. Nice thing.
24. That should keep you busy for a little while. Ah, you might as well throw 27 in there as well. You got stuff to do, ladies and gentlemen. Go to work. I'm here if you need me. Feel free to call me over. Or feel free to wake up and at least try these problems.
So we can Wait, 2.64 grams of hydrogen gas is not nope. Oh yeah, it literally says walk by. Please. It's okay.
Thank you.
Might go, Mr. Gray.
Yeah.
Oh.